I want to show you the reason that ladder logic diagrams are set up the way that they are. This is a schematic from a heat pump that I bought many years ago. In fact, I bought multiples of these heat pumps. They came out of a hospital, and I don't know what hospital they were from or anything about them. They were just 1-ton heat pumps, which all that means they didn't weigh 1 ton. I was able to move them myself. All that means is that they were able to, well, they had a refrigeration capacity of 1 ton. When you go through a thermo class with me, you'll understand what that means. It's just how quickly it can cool something down or heat something up. Anyway, inside of each of these devices there were schematics, and it was really handy because the schematics explained how the electrical side of the system worked. And it was easy to understand. Once you looked at it and you thought about it and you kind of looked around to see what components were present, then you could tell what was what. Now, I'm going to zoom in on this, but before I do, notice that this is set up and it looks a lot like a ladder logic diagram where there are rails on the left and right, and there are rungs going across. So I'm going to zoom in on this, and also notice that there's sort of an upper ladder and a lower ladder as well. Let's try to understand what this is. So when we zoom in on it, there's something about note 2. We'll see what that is in a minute. But at first what you notice is that it says 208-230 volt, one phase, 60 hertz power supply. So this is telling you what the electric potential needs to be across L1 and L2. L1 is the left rail, L2 is the right rail. And that's an abbreviation for leg, basically a leg of power is the way you'd think of it. It's just one of the terminals. Think of when you plug in something to an outlet in a wall, that's 2 legs basically. Technically it's a leg and a neutral, but in our case these are 2 hot legs, and what that means is both are varying their voltage against neutral or ground. The first component you might notice on the first rung is this compressor labeled COMP, and that compressor looks like can be turned on. You notice there's a switch with coils, or not coils, but with contacts labeled CC. We'll see what that is here in a minute. But it makes sense that COMP is the compressor. You notice that there's a line inside of the compressor on the C terminal that comes down and goes over to the right, down, over to the left, and then down. That looks like a temperature switch. That's a temperature cutout. So that means that this compressor has a thermostat, basically, something that opens up if the compressor overheats. Another nice thing about this, at least for the sake of repairing such devices, is that there is a indication of the wire color. So you see the black wire color there, and then blue on the right as well as red on the right coming out of the compressor. It's not really coming out of the compressor, it's just these are the connections to the compressor. And then there's CRC, and that kind of looks like a capacitor. It kind of looks like a set of contacts. Turns out it is actually a capacitor. I'll show you that in a minute. And then on the right hand side there's another CC. So what you notice is that there are switches on either side of the power rails going to the compressor. And unless both of those switches close, the compressor will not run. On the left hand side after the switch there's a point labeled T1, and on the right hand side after the switch coming towards the compressor there's a label T2. Those 2 labels indicate points in the system, points that would be labeled, say, on the coil contactor. That's probably what CC stands for. If we look up CC, there's another diagram off to the side. We'll have to scroll over to it. And it shows you how the various components are laid out. There's several electrical components that are important. One of them is that coil contactor, and so you notice right in the middle of this box there's the coil contactor. It's showing you mechanically how it's laid out in the electrical box. So that's one item. You notice that there are several others. There's the CRC. It turns out that is a capacitor. That most big motors like this or larger motors need a capacitor to start and run. Certain types of motors need it regardless of their size. So this CRC capacitor, that's a start capacitor. May even be a run capacitor. It doesn't show any way of it being taken out of circuit, so it must be a start and run capacitor. What else have we got in this diagram? Well, if we move down to the next rung, there is something labeled PLCR. What is that? Well, let's see if we can find out. Now we could go up here and we could probably find it. Let's see, PLCR, except I don't see it. Here we are, PLCR, Power Line Carrier Receiver. Well, what's that? Well, if we go down to the bottom, Power Line Carrier Receiver Hookup. So this is just the way you hook up power to the unit, essentially. We're not too worried about all of the details in this. So this would be some type of a device that would sense, I suppose, when the power is applied. What else have we got? Well, this is a blower motor. So this is a motor, there was a fan in the unit that when the compressor was running and pumping heat, the blower could be turned on to, exchange that heat with surrounding air. And there were 3 different wires coming out of it. There was a high, medium, and low, which were color-coded black, blue, and red, that you could use to choose the fan speed. And it wasn't set up to switch between them automatically or anything. You just wire in the one that you want. And then there was a relay, basically, that the contacts here, BR, could be activated to turn on that blower. And they show orange note 6, and then they've got purple, brown, and then a capacitor here. It turned out that these things were for the actual voltage. Remember up here it said that the unit could take 208 or 230 volt. And I guess the compressor wasn't really sensitive to which one it ran off of, but the blower was, and so you had to choose the correct wire to connect here. There are many other things here. Let's skip down, though, to the bottom of the diagram, and you'll notice there's a transformer here. You see the control voltage that's commonly used on these HVAC type systems is 24 volt AC, and you've got to get it from somewhere, and it's best just to take the power that comes in, the 230 volt AC, and convert it down to 24 volt DC. And then you'll notice that we're powering another ladder here, right? There's a rail on the right side, essentially a rail on the left, but it looks a little bit different. Now you'll notice that the coil the coil for the blower motor is down here on the last rung, and then the contactor for the compressor, CC, that coil is up here on a separate rung. And there's several different switches that have to be on for the coil for the compressor to run, so that the switch for the compressor is pulled in and gives power to the compressor. And you might say, well, wait a second, this doesn't make sense. Why wouldn't you just take all these switches that are in a row and connect them directly to the compressor? Why put that coil in there as an intermediate device? Well, there's a couple of reasons. Number one, the switches are not made for carrying a whole lot of power. If you make a switch that carries a lot of power like that contactor, it costs more. It takes more material. It's less reliable. It's better to switch low voltage on and off with all of your sensors than to switch high voltage. But another reason is that we need control over the compressor. We need some way of turning it off, and so the coil contactor, that relay essentially, is ideal for that purpose. And so you'll notice that there's a wire, let's see, you've got a couple of options. You can either connect up to this terminal here, and I don't remember why that was the way it was, or you connect it directly across here to Y2. So you could short out between this point and point 1, or you could connect to the other two. The point is that you needed to have a control signal where you could turn the compressor on and off, because you've got a thermostat sitting on the wall, right? You want the thermostat to control the heating and cooling, and so that thermostat should be able to turn the compressor on or off. So even though we haven't figured out everything in this diagram, we could, but there's not much of a point. My reason for showing this to you was to show you that when you see a circuit like this, it's pretty easy to understand. But what about when you see a circuit like this? If you see the circuit actually in operation, there's lines on the board going every way, and you can take a multimeter and perform continuity tests and figure out what's connected where. But understanding what the circuit does and what could possibly be wrong if the circuit's not working properly is very difficult. On the other hand, a layout like this is easy to follow and understand, and you can figure things out because it shows you the nature of the circuit, how power wants to go from one rail to the other, or not power, but current wants to flow from one rail to the other, and it's all the intermediate devices that can turn on or off and either allow that current to flow or not, so that current can drive them and do useful things for us. So this layout is easy to understand, and for the sake of electricians, ladder logic is laid out as it is, so that even electricians who haven't necessarily had a lot of training in PLCs, maybe they have, maybe they haven't, it varies, can understand it and troubleshoot and figure out what's wrong and make things work right, or even write a fairly straightforward program. PLCs are typically not, well, today they're used more, but originally they were intended to control fairly simple things. They were supposed to be simple devices that were easy to understand and use and easy to make a program to control and automate machines. Another diagram I posted for you is this is an old version of the program that I run in my PLC for controlling my heating and cooling system. And I'll zoom in on this. I'm not going to go through the whole thing. I'll zoom in on it and show you a few things. The compressor is a two-stage compressor instead of being a single stage, so you've got a high load and a low mode. And when the thermostat correspondingly can call for high cool or high heat, low heat. And you'll notice on the first rung that when the thermostat is calling for low cool, as long as the compressor is not in a rest state, that's the next item over C1, then the low stage of the compressor can turn on. Now, if any of those are not true, then that output instruction has complete control over that output, and it will shut off that output. There's another rung down. Let's see, 1, 2, 3, 4. The fourth rung down shows the high stage compressor output, and these are just where you give 24 volts AC to the compressor on these certain points, and I've got it all wired properly so that when 24 volts AC appears on those points, then the low stage compressor's turned on through a contactor. Same thing with the high stage. But there are some other conditions. For example, the thermostat may call for low heat. Well, from the compressor standpoint, if the compressor is what's going to be used instead of as an air conditioner, if it's going to be used as a heat pump because the reversing valve is on, then again the low stage compressor should come on. And so you notice that there's a condition in the branch, sort of an OR condition, if the thermostat is calling for low heat and the boiler is not ready. So you can start to read this almost like it's English. So if the boiler's not ready and the thermostat is calling for low heat and going up to the rung, the compressor is not in a rest state, then turn on the low stage compressor. Now, if you understand this, great. If you don't worry about it. This is just what a ladder logic diagram looks like, and this is a real program. It's a little bit smaller than the one I use now. I've added more to it because I've added more to the system. But what this program basically does is select between multiple heat sources for my home. I've got a boiler that runs, and so it might be ready. It might have thermal energy available to heat the home. I've got tanks that store hot water because it's actually more beneficial to run the boiler at full tilt and burn wood as quickly as possible, and it just squirrels away that thermal energy into water in tanks. So I can pull from that, or if it's warm enough outside, just run the heat pump. And so depending on what's ready and what's available, and that depends on temperature outside and other things, but I would have this program set up to select which heat source to use. So this is just a real ladder logic diagram that's kind of nice to me because it keeps me warm every winter, and thought you might like to see it and see how it relates to a regular electrical ladder diagram.